Thank you very much for the opportunity to be here and give this talk. I will indeed tell you about recent developments in formal supersymmetric quantum field theory. And my talk will highlight three major themes. The first is the classification problem of superconformal field theories. The second is exact calculations. These are really the bread and butter of supersymmetric quantum field theory. And finally, I'll discuss some new connections between supersymmetric and non-supersymmetric dynamics. And let me also add a standard disclaimer. Supersymmetry is a huge subject, and this talk is an incomplete survey of a few exciting directions. Okay, so what's the classification problem? Broadly speaking, the goal is to classify superconformal field theories. And of course, this gets easier as we add more and more supersymmetry. And we could start there. And with less supersymmetry, it might be a meta problem that we could never really completely solve, but we could try to organize. Why is this problem interesting? Here are three reasons. The first is that superconformal field theories are highly symmetric universality classes. And so understanding them is a starting point to classifying dynamics of quantum field theory in general. Another general theme is the connection to mathematics. So supersymmetry from its inception has been deeply linked to mathematics, and new results in supersymmetric quantum field theory might directly lead to new math. And finally, there's a holographic motivation, which is that learning about superconformal field theories teaches us about non-perturbative constraints on quantum gravity. So let's start with an overview of the status of maximal supersymmetry. So we know that superconformal field theories can only exist up to space-time dimension 6, and they have a maximal number of Poincare supercharges, which is 16. So in space-time dimension 6, we have a good working understanding of what all of these theories are. These are the so-called 2-0 theories. They admit a conjectural ADE classification, a Lie algebra classification. And we believe that the SUN type is constructed by M5 branes. That's been the standard belief for some time, but there is new progress in the last 10 years, understanding this by the conformal bootstrap, for instance. For instance, we know about the minimal central charge theory quite well from that approach. Now, the most well-studied maximally supersymmetric theory is n equals 4 super Yang-Mills, the case of space-time dimension 4 with 16 supercharges. And here we believe we have a list of what all the theories are. They're just maximally supersymmetric Yang-Mills theories with various gauge groups. But this is, in my opinion, a kind of conjecture. And it would be interesting to know if we could really prove something like that. Could we really start just from the superconformal algebra and the constraints of symmetry and establish that these are all the theories that exist? Now, one kind of hint in that direction is that we know just from symmetry that any such theory has an exactly marginal coupling tau. And we know the geometry of the Zamolodchikov moduli space, of this coupling constant space. And the infinite distance limit in this moduli space, we believe it should have higher spin conserved currents, and therefore should be the free weakly coupled n equals 4 super Yang-Mills that we know. And more generally, this kind of idea about higher spin conserved currents at infinite distance limits in moduli space is believed to hold quite broadly and is connected to recent swampland ideas. Now, if 6 and 4 dimensions are understood quite well, 3 dimensions is pretty wild. So kind of the modern revolution in 3-dimensional maximal supersymmetry was started by Bagger, Lambert, and Gustafsson, who wrote down these Chern-Simons theories. They have 2 gauge groups, SE2K and SE2 minus, level K and level minus K. They're Chern-Simons theories. And they have some matter encoded in that quiver. And these are maximally supersymmetric for any K. K is the level. And small k describes the world volume theory of 2 M2 branes. But for general K, there's no known string theory construction of these. So that's an interesting open problem. subsequently, A, B, J, and M found Chern-Simons descriptions for the low energy limit of maximally supersymmetric super-Yang mills with various classical gauge groups. So these are examples of maximally supersymmetric theories in 3 space-time dimensions. And I'd like to stress that this list is definitely incomplete. For instance, we have no candidate for the low energy limit of exceptional groups, maximally supersymmetric Yang mills with exceptional groups. But it's also redundant in that there are non-trivial dualities relating various elements on this list. So I think it's an interesting big problem to try and figure out what is the set of maximally supersymmetric 3-dimensional quantum field theories. And we don't really have an idea about that yet. So we're not just interested in classifying theories, we're interested in understanding their dynamics. And here there's some really interesting recent progress in 4-dimensional n=4 theories that I'd like to give a brief overview of. So much of the new progress comes from studying integrated correlation functions and understanding the implications of S-duality. So here, for instance, is an example of an integrated correlation function of 4 local operators, L and M. We've integrated over their positions, and the result is some function of the coupling. Now, this quantity can be computed exactly using supersymmetric localization, and it has a remarkably simple S-duality kind of covariant form. So B of t here is some known rational function. Now, what's interesting about this, this correlation function is that you can take it as input and start constraining non-supersymmetric observables quite well. So for instance, these authors here use this integrated correlation function to study the dimension of the lightest non-BPS scalar. This is the Konishi operator. And here's a plot I've taken from their paper. So this curve here is what you get from the superconformal bootstrap, taking this as an input. Another really interesting result in n=4 recently is to kind of harness the full power of duality directly. So in early results in studying duality, people look for evidence of duality. But now we're a little more grown up. We're going to take duality as a given and see what it teaches us about dynamics. So one thing that you can do is you can use a kind of harmonic analysis. So any observable O, which is a function of tau, this could be a correlation function, partition function, whatever you want. If it's invariant under duality, it has this kind of expansion in terms of known modular quantities. These are some Eisenstein series and mass forms. And so this is a very deep idea that quantitatively links perturbative and non-perturbative physics. And you can do a lot with it. It's just being explored. I think this paper is from last month. It's one thing you can do is you can learn something fundamental about quantum gravity. So this suggests that using this formalism, you can see that ensemble averages over couplings, that is tau, at large n are equivalent to the infinite coupling Tuft limit, and that both are holographically dual to type 2b on ADS5 times S5. So this is had been a kind of open problem to understand these puzzles in terms of wormholes, and this is an example of a supersymmetric QFT providing some fundamental conceptual insight into that question. Okay. In general, when we go to space-time dimension larger than 4, we encounter much more mysterious and less understood phenomenon. There are various approaches to studying these theories. One prominent approach that we'll hear more about later is geometric. So you can study string theory solutions which can support some kind of localized conformal field theory. And the general idea is you have string theory and some geometry, and then some singularity develops. Here I've drawn it as this neck collapsing. And at this singularity, string theory supports some trapped quantum field theory degrees of freedom. Now, the nature of what kind of field theory you get depends a lot on the details of this collapse and what you started with. And there's a rapidly growing dictionary working this out. So for instance, if you want to develop a 6D quantum field theory, you want some singularities of an elliptic Calabi-Yau manifold. In 5 dimensions, it's more intricate. You want a collapsing 4-dimensional surface. And it's in general an open problem to classify these singularities and relate these 5- and 6-dimensional constructions. And I believe there's a lot of ongoing work on that. And relatedly, the holographic approach to studying these theories at large N, all ADS7 and ADS6 solutions of type 2 string theory with supersymmetry have been completely classified. Now that previous slide is an example of the kind of tight dictionary that exists between geometry and supersymmetric quantum field theory. And throughout, there's this idea that if you construct a field theory via string theory or compactification, you'll always get some kind of geometric type interpretation of any supersymmetric observable. And in 4 dimensions, this was modernized by the class S construction involving reductions of fibrils on Riemann surfaces. But it's a huge industry right now developing this dictionary between geometry and supersymmetric quantities in field theory. So let me just highlight a couple recent developments. So one is that using ideas like this, you can find explicit Ricci flat metrics on the K3 manifold using BPS states. So K3 is the simplest Calabi-Yau, and for a long time, we didn't know how to describe its geometry, but there has been some exciting recent progress on that. And another area of interplay between geometry and physics relates to 3-manifold topology and ideas of higher symmetry and vertex operator algebras. Now, there are also moduli space methods, complementary methods to study quantum field theories in general. So here we study the supersymmetric moduli space where we preserve Poincare supersymmetry. So an example of a recent application of that is to study QFTs in 6 dimensions. We can look at their trace anomalies, so the trace of the energy momentum tensor. It has some conformal anomalies, which are A and Ci. And these gives us some exact results about 2, 3, and 4-point correlation functions. And recently, there has been some kind of cumulative progress on understanding how to compute these universally, and also how to show that these class of theories satisfy general expectations of the renormalization group. So for instance, one can prove, just using this supersymmetric structure, that the A anomaly is positive, and along any supersymmetric RG flow, AUV is larger than AIR. So this is kind of remarkable. We don't know any direct Lagrangian formulation of these theories, but nevertheless, we can bring them under the umbrella of the renormalization group flow. The pinnacle of moduli space methods, as they are currently understood, is in 4D n equals 2 quantum field theory. And here there are, broadly speaking, 2 approaches. There is a Coulomb branch approach, where one studies the low energy limit where theories look like abelian gauge theories. And this is constrained by the Seiberg-Witten geometry. And there is an industry understanding the possible geometries that one can obtain there. And second, there's also the Higgs branch approach. The Higgs branch is closely connected to a set of protected local operators encoded in a so-called chiral algebra. And there's a tight interplay between these approaches. So there's an interesting recent match between vertex operator algebras and low-rank examples of Coulomb branches. And one thing I'd like to highlight is that both of these ideas, they connect the moduli space geometry, the set of supersymmetric vacua, to intrinsic CFT correlation functions and data. And this is something that we understand pretty well in this class of examples, but it would be very desirable to develop this dictionary for other dimensions and other amounts of supersymmetry. Okay, I also want to briefly mention supersymmetric defects. So it's being increasingly understood that there's more to quantum field theory than just local operators. So there are line operators, surface operators, domain walls, boundaries, etc. And for example, understanding these extended operators is crucial to making progress in thinking about generalized concepts of symmetry. We'll hear more about that soon in another talk. And supersymmetric quantum field theories provide a very controllable arena to learn about these objects. That's in general theme about supersymmetric quantum field theories. Whenever there's some new conceptual development in QFT, often it becomes first most quantitatively precise in the context of supersymmetric field theory. So here there are various ongoing works and results. For instance, there's a classification of supersymmetric defects and analogs of A theorems. And there's also interesting examples of defects with exotic fusion algebras from S duality and higher form symmetry. Okay, the last topic I'd like to mention is connections between supersymmetric and non-supersymmetric dynamics. So many of us get into this subject thinking that we're going to understand supersymmetric field theory better, and that's going to directly help us understand the dynamics of non-supersymmetric field theories. And it's interesting to understand to what extent is that just a dream and to what extent is it really quantitative. So let me tell you about some approaches to make it more quantitative. So in 3 dimensions, this is where this idea had its modern rebirth. There's these famous dualities, so-called mirror symmetry. So here's an example: U1 with 2 gauge theory, U1 with U1 gauge theory with 2 hypers. We know something about its infrared limit, and it has a direct non-supersymmetric analog. And you could ask, can we directly map between these 2 kinds of dynamics? And indeed, this has been explored. So there's a direct link at large n, in large n Chern-Simons matter theories, and it's also been explored at small n using soft supersymmetry breaking. So what is soft supersymmetry breaking? This is where you add some kind of mass term to a SUSY Lagrangian to remove some fields. So you take your Lagrangian to be of a general form where there's some supersymmetric piece, and then there's some supersymmetry breaking piece that removes some fields that you don't want. And you hope that you can use supersymmetry to study this problem. And of course, your challenge will be that you understand small m using supersymmetry, but what you really want to know about is large m, which is the non-supersymmetric theory. But nevertheless, you can use this often to gain qualitative insight about the infrared dynamics of non-supersymmetric theories and hope that there's, for instance, no phase transition as you crank up m. So there are 2 recent examples in 4 dimensions where people have exploited this idea with some success. So one is 4-dimensional adjoint QCD. So this is QCD where instead of having fundamental quarks, we have adjoint quarks. So let me talk about the case where we have 2 adjoint quarks. They have an SU2 chiral symmetry. And the standard lore would be that there's confinement and chiral symmetry breaking via chiral condensate, and that this should lead to a nonlinear sigma model of Goldstone bosons on the 2-sphere. And this can be studied by thinking of this as a limit of n equals 2 super Yang-Mills, where you, in addition to the fermions, you would also have some adjoint scalars, which you would remove by soft supersymmetry breaking. And this, in this example, by doing that, you find a direct link to this confining phase from this Seiberg-Witten solution via condensation of monopoles. So this is an example of confinement via dual Higgs mechanism. Now, of course, another very interesting example, a target for these ideas, is to try and understand the dynamics of QCD directly using our detailed understanding of n equals 1 Seiberg duality. For instance, we could ask for the range of NF and NC where one has chiral symmetry breaking or a conformal window. And recently there has been an explosion of activity in this direction, pioneered by this group of authors. So the idea is in the general paradigm that I outlined before, they're going to deform n equals 1 SUSY QCD by some operator that gives bare mass to gauginos and squarks. And then this is going to be tracked to the infrared using the fact that the operator in question appears in the supercurrent multiplet. And this kind of technique is sometimes called anomaly mediation, this fact that this operator is special. So in the infrared, this deformation, together with the moduli space potential, generates a minimum with chiral symmetry breaking if NF is less than 3/2 NC. So here I've pulled a plot from a paper by Moriyama, where this red, this is for NF less than NC, where supersymmetric QCD has a runaway at long distances. This red is the supersymmetric Affleck-Dine-Seiberg potential, and this blue curve is the potential where we add this deformation and see a minimum. So this is kind of hot off the press, and it's very exciting to understand the reach of these ideas and what else we could do with them. Okay, so let me come to my conclusions. So I hope I've convinced you that the universe of supersymmetric field theory is vast and growing, and each theory is a potential playground for mathematical physics. There are new exact results all over the place teaching us about the guts of quantum field theory and quantum gravity. And finally, there is more to explore in the relationship between supersymmetric and non-supersymmetric theories. Thank you.
Thank you, Clay, for this impressive overview that was delivered in exactly 20 minutes. Are there any questions from the audience or from Zoom? Yes.
So in these cases where you take a supersymmetric theory and deform it, you said that you hope there's no phase transition as the mass terms become
Yes.
comparable to the phase transition scale.
Yes.
Is there any guiding principle for trying to think about when there may or may not be a phase transition, and what types of deformations one might think are more robust?
No, I think that is a really great question. I mean, there are certain things you can do to try to help yourself. So the first thing is that if you want to have any kind of control at all, it's important that that mass operator be part of a short multiplet of supersymmetry. If it's just some random operator, supersymmetry is not going to help you with anything. So for instance, in the example of Adjoint QCD, the thing that removes the scalars is part of the energy momentum tensor multiplet, and so can be found at low energies. And that's roughly speaking the same thing that happens here. The deformation in this case is part of the Ferraro-Zumino energy momentum tensor multiplet. So that's one thing you basically have to do. But I think it's not really understood. I mean, one case where you can probe this question directly is at large N, where the flow by soft supersymmetry breaking is quite short. So you can see kind of directly that nothing bad is happening. But I don't think we have a good understanding of it in general.
Eva.
So thank you for the very interesting talk. So you've brought up this relationship to mathematics and also the relationship between supersymmetric and non-supersymmetric QFTs. So in mathematics, there are manifolds which have moduli, but more generically, the manifolds you might consider mathematically are rigid. So they and that's a very big distinction. Mathematicians can study both cases, and they do study both cases to great effect, often using very, very different tools. So how do you think about that, making the jump from, say, mathematically manifolds with moduli to manifolds without? Do you think of it in the same kind of way you're thinking about making these connections between SUSY and non-SUSY, or do you think of it as a bigger kind of leap, if the question makes sense?
I understand what you're asking. I mean, it's certainly possible if you were studying this relationship that there might, in some cases, be no connection. It's possible that there's dynamics that's allowed without supersymmetry that is forbidden by supersymmetry. So in some sense, to have these direct connections like this, we have to get a little lucky. But I think it's worthwhile to quantitatively try.
Any other questions?
What's your perspective on the interplay between, say, analytic methods like this and information from lattice gauge theory?
That's a great question. I would love, and maybe people here will tell me that it's already the case, but I would love lattice gauge theory to be a tool that I could, even if I don't understand it very well at the level of the numerics, that I could use to, say, probe a new duality. I have a conjecture for some set of supersymmetric fields is dual to some other set at long distances. I would love there to be a lattice-like tool which would allow me to compute some non-protected observables directly to some accuracy and check whether that's the case. So I think, and I think I'm not the only one who would really like that kind of tool. So that's something where I think there could be really direct crosstalk. Sometimes there are theories that are interesting to us that have more practical, that can be simulated more easily. Like for instance, this example where you have one Dirac adjoint. This is something which I think could be simulated quite straightforwardly. We have some ideas about what the low energy of that is. So I think there's room for improvement in the relationship.
This is just a follow-up to Lance's question. What are the lattice computable observables in this theory that you are most interested in this particular theory?
In this adjoint QCD theory? Yeah, so I mean, you can come up with, for instance, various possible infrared candidate phases for this theory, which match all anomalies and symmetries and things like that. So one is this spontaneous symmetry breaking phase, but there are others. And so, for instance, I'd like to understand, to first approximation, I'd like to understand if this guess, this lore is actually correct. Like, is there a, what's the low energy just spectrum? That would be the first starting point. The massless spectrum, even.
Just a quick comment in relation to the last two questions. One thing you may not be aware of is that there is a lattice formulation of n equals 4, which conserves a certain amount of supersymmetry. And yeah, just recently, there's been a sort of a minor breakthrough in being able to push those lattice simulations to very strong coupling, where you can look at things like the Konishi scaling dimension, things like that. So that's something that is possible to provide some input here.
Yeah, I mean, that would be great. For instance, there's this very recent analytic work saying that this is what the dimension of the Konishi looks like.
So that would be great to check with lattice simulation too. And certainly in the context of the other model you were talking about, there was a lot of work done a few years ago on the case with 4 vial fermions in SU2. I'm not so sure whether the studies of the 2 flavor case, maybe Ethan would know better than I would. There may be a sign problem there. I'm not sure. Just a comment.
Anything else?
If I could selfishly ask a quick question, maybe also flowing the other way, is there anything we can learn from supersymmetric gauge theory is useful for the lattice? So, there's David Tong's story about chiral, non-chiral duality being a way to get access to chiral fermions. Anything in that direction you'd like to comment on?
Useful directly for the lattice. You mean basically a lot of that is, I think generally speaking, that we have a lot of examples of strong coupling dynamics that can generate mass gaps in interesting ways, even in ways that might look naively forbidden based on kind of weakly coupled lattice arguments. So I think that Tong's example is a good starting point, but generally speaking, there's a lot more. So yeah.
Thanks.
Okay, one last question perhaps I can ask. So you mentioned that there's this interplay between the moduli space analysis and the algebra of correlation functions at the conformal point. The one comment is that it's still very mysterious. We have certain relations, but we don't understand the conceptual underpinning of the correspondence. In fact, one of the most interesting clues, perhaps you are too modest to mention, it comes from your paper with Shuang Shao, when one can relate certain intricate wall crossing invariant the Coulomb branch with the circumformal index, and I think it's fair to say still an experimental, mysterious observation. If you have any thoughts about that.
I mean, I have some thoughts about that conjecture in particular, but let me just say that I emphasize that I think this is a very important problem to understand exactly why the moduli space of vacua is connected to fixed point data at the CFT. And let me just be even more, a little more wild and say that if you change the space-time dimension, it's going to get much more bizarre. I think, for instance, in higher dimensions, the moduli space is connected to extended operators, not to point operators. So the dictionary will have to be quite involved.
Thank you. I think we are out of time. We can thank Clay again for this beautiful talk.